definition 109, this is going to be a specific function which adds 1 to things. So that's pretty much the only kind of addition that we have a notation for, is this successor notation. So it's going to be a function consisting of all of these pairs n comma next n, running over all natural numbers n. So this is a function that, given a natural number, gives you the successor, the next one. And I just want to give it a name. That's why this is a definition. I want to give it a name so that I don't have to write this every time. So we need a nice symbol. And for this, I just made up a symbol. And it's this symbol. It's supposed to look like plus plus, like 2 plus signs on top of each other. But, you know, interpret whatever you want. So that's our adding one function. So I think it's okay to just make up a symbol because this is totally temporary. Pretty soon we're going to have full-on addition, and we'll just be able to actually talk about, you know, adding one like this. So this is just temporary. Okay, now you might object and say, don't we already have a notation for this? Next. Doesn't next act to add one to things? Why this new notation? Well, next is actually not really a function. In fact, it's not anything. If you write this, it's not a term, it's not a proposition, it's nothing. It's just not even a part of the language. So to write this is as ridiculous as, you know, breaking apart a letter, like, you know, writing a letter I and then trying to ask what is the dot? It's not anything. It's just part of a larger mark, and you shouldn't look at it by itself. The next is part of a larger marking, which is when you write next parentheses and then a term inside, like this. So it's kind of like when we define the notation for power set, this fancy p parentheses x. We didn't define fancy p as something on its own, right? We just said if you have any term, not necessarily a variable, but if you just have any term, then you can put a fancy p with parentheses around it, and then overall you will get a term. It's the same with next. So next is not really a function. For example, you cannot talk about next mapping n to n. It's not an object of its own, because you can't even talk about next by itself, you know? Okay, hopefully that makes sense. So now we've got something that actually is an object, and we can throw it around and do stuff with it. So for example, this thing actually maps n to n. It has a domain. This is an assertion. This is a proposition. It says 3 things. It says this is a function, its domain is n, and its range is a subset of n. So this needs some proof, but it's not too hard. So first of all, the actual definition of this thing, this is written in kind of a shorthand, right? Since what you see here behind the bar is not a pure variable. The actual definition is going to be something like this. The set of, let's say, p for pair, such that there exists n, such that p is n next n, and n is a natural number. So it's really a shorthand for this. So just to get practice with some of these old ideas, let me quickly put up proof that this is a function. So suppose you've got 2 pairs in there with the same first coordinate. Then because they're in there, what do we know about them? We know that this holds for them, right? So think about, you know, axiom 5. Think about these playing the role of p. So this statement, but with each pair being in the position of p. Then existential instantiation, we can get, for this existential quantifier, we can get n and m such that xy is equal to next n, and xz is equal to, n next n, and xz is equal to m next m, and n and m are natural numbers. Then the goal is to prove y equals z. So then we'll, by essence of pairs, x is n, but also x is m, right? So n is m. Then y is next n is next m, just because n is m, is z. Next m is z. So this is a function. All right, its domain is n. Let's see. So let's do double inclusion. Let n be in the domain. Then by the definition of domain, we can get an m such that the pair nm is in there. Then using the definition of this adding one symbol, you know, the one here, to say that this pair is in there is to say that there exists some, let's call it k, such that our pair n comma m is k next k, and k is a natural number. So we can get k a natural number such that this happens. Then by our essence of pairs theorem, n equals k, but k is a natural number, so then n is a natural number, and that proves this inclusion. Then for the other inclusion, let n be a natural number, and then we try to show that n is in the domain of our adding one function. But if n is a natural number, then the pair n next n is in our adding one function. Let me go ahead and just use the shorthand to justify that, although really it's an existential generalization. So, well, that's enough to tell us that n is in the domain. That's another existential generalization. And then finally, range is a subset of n. So let n be in the range, and then we'll try to show that n is a natural number. And we should be able to get an m such that mn is in there by the definition of range. Then, using the full non-shorthand definition of our adding one function, to say this pair is in there is to say that there exists a k, so we can get, by existential instantiation, a k natural number such that this pair is k comma next k. But then, by the essence of pairs idea, n equals next k. Remember, our goal is to show n is a natural number. So the task reduces to showing that next k is a natural number. And is next k a natural number? Yes. I guess it deserves its own sentence. Next k is a natural number because n is inductive. Right? K is a natural number, n is inductive, so n contains the successor, the next, of anything that it contains. So it contains next k. And that's it. We now have that n is a natural number. So that proves, what does it prove? It proves this mapping statement. We now have this object we can throw around which actually maps the natural numbers to the natural numbers. So really all you need to know about it is that it maps natural numbers to the natural numbers, and it has this formula that its value at n is the next of n. And we could totally have defined it by this formula to begin with, but I just wanted to show the justifications for why defining something by a formula actually works. We really haven't done that enough in this course. So now I want to make a list of some functions that we found. Right now we've found just one function, a function that adds 1 to things, and it's this function. So this is a function that when you apply it to something, it gives you the next one. When you apply it to a natural number, it gives you that natural number 1 more. So it steps, you could think 1 to the right. Do we have a function that adds 0? So do we have a function that adds 2, that adds 3? Can we build these, and what do they look like? So when I say what I'm trying to put down in this list is all things that map n to n. So like this belongs here because it's a function mapping n to n that sends any given input to that input plus 1. I shouldn't say plus 1 since that's what we're actually trying to define, but let's just say it sends any given input to the immediate successor of that input. Now what about something that, quote, adds 0? That would be a function from n to n that does nothing, right? That sends everything to itself. We know somebody by that name. The identity function on n, right? The identity function on n is this collection of pairs. It just sends every natural number to itself. If you look at what it does to an input, the answer is nothing. It just gives you that input back. So there's our adding 0. How about adding 2? So by adding 2, what I mean is a function that when you give it an input, it gives you the next of that input when you give it a natural number input. So it should be a function whose value at n, so let's see, whatever goes here in the adding 2 position will be some function, n to n, and when you give it something, it gives you the next of that thing. So in other words, this is a way of writing next n, and then it gives you the next of that, right? So what's f in this situation? F would be this composition, right? If I want to do one function and then do another function, or do one function then do the same function again, composition is what I want. That's how you do functions in succession like that. So here's our adding 2 function. And then what about our adding 3 function? Well, take our adding 2 function and then follow it by another adding 1 function. And now writing things this way, you can see that there's going to be a pattern that could possibly be continued. So you can guess what adding 4 would be, and so on. Each time you want to come up with the adding the next number function, you just compose with another adding 1 object. Starting point, and you can see the recursion rule, right? Each time you compose, even here, this is actually being composed with the identity, right? You can view them as all starting up here, since composing with the identity effectively does nothing. That's why we call it the identity. That was one of our earlier facts about the identity. So you can see we have our starting point, we start at id n, and then our recursion rule. At each stage, compose on the left with another copy of our adding 1 function. This sequence can be actually this pattern, or this thing with the dot dot dots, if you explicitly describe the recursion rule, then this, thanks to what we've proven today, and the part that we didn't prove also, thanks to theorems 107 and 108, thanks to these guys here, this actually defines a sequence of functions. And that sequence of functions we will call add with some fancy letters. And next time we will build this up a little bit more carefully and use it to define addition. So we'll define a plus b to be the adding b function applied to the input a. So that's next time.